All right. Welcome, everyone. Today, I'm going to present our work, Dense Defense, Diversity Promoting Ensemble Adversarial Trainings for Effective Defense. I'm Onat Gungor. I'm a PhD candidate at the University of California, San Diego and San Diego State University. These are my advisors, Tajana, and Baris. So let me start the presentation by the motivation of data-driven predictive maintenance. So in this work, we propose a novel defense mechanism against adversarial attacks for data-driven predictive maintenance. So what is data-driven predictive maintenance? So data-driven predictive maintenance utilizes historical sensory data to train a learning model. So this learning model can be a machine learning model and try to predict remaining useful life of a machine. So you can think this as a machine production system. So this is only one application, right? Remaining useful life estimation. So here in this framework, the data quality of this sensor plays an important role in machine learning prediction performance. So this is a really great case, optimal case, where we do not have any intruder. But what if we have an adversary, right? If we have an adversary, that adversary can conduct one type of adversarial attack. So we call this adversarial attacks against machine learning model, meaning that the adversary can obtain some information, can utilize some information about the machine learning model to create what we call perturbed input data. So these are created in a clever manner so that it's not easy to detect by the detectors. Small perturbations can lead to really bad consequences. So misleading useful life predictions. So this can lead to undetected failures in a production system, which can cause huge losses. Right? So that is why, so this was our motivation. So that is why we need an effective or novel defense solutions that can protect our production systems against those attacks. So adversarial training is one of the most efficient, effective defense approaches proposed in the literature, which is pretty common in computer vision field. So the idea is simple. So instead of training machine learning models by only using clean data, we will include some perturbed data into the training process. Right? So that when we see a perturbed example later, our model can be fast against those. However, there's one main drawback of adversarial training, which is our model is only robust to examples created by same or very similar methods. So one improvement to solve this problem is what we call ensemble adversarial. The idea is again, instead of using single method to create those examples, let's use multiple models. That is why, that is how we took, in terms of adversarial perspective, it's even harder for the attack to create multiple models. We need to satisfy one condition, which is ensemble robustness. We need our base learners to be as diverse as possible. So how do we promote the diversity against base learner? Is through promoting the orthogonality between gradients of base learners. Inspired by this, we try to select our optimal base learner subset of base learners by looking at the similarity among the loss gradients. So here's our proposed framework. So we assume that we have pre-trained models from our previous study. These are deep learning models specialized for time series prediction. We first calculate loss gradient similarity in a pairwise manner. Here we use cosine similarity. Then we end up with a table like this, which gives us pairwise similarity. Okay, the smaller the similarity, the more diverse the models are. Then we select, as I mentioned, subset of models which are as diverse as possible. And then we create an augmented training data, which is represented in green color. So here we use fast gradient time method, which is one of the methods to create an adversarial example. Okay. Then we train a convolutional network, one-dimensional convolutional network, due to its great performance, remaining useful life estimation. And as an output of this proposed framework, we obtain adversarial trained So let's go through each step. So as our pre-trained models, we have used 10 different deep learning models from our previous study published in Computer Industrial Journal. So the first architecture we have architecture from which we have used basic recurrent unit, kernel network, long short-term memory, and some variations of those. Second category, second architecture, we have in which we use one dissimilar. We also have some hybrid architectures which combine two models to improve prediction performance. Okay, let's continue with the loss gradient similarity calculation. As I mentioned, we measure the similarity in a pairwise method using cosine similarity. Here in this formulation, delta or G refers to the loss gradient vectors of base model F and G. By the way, base model represents a single model in an ensemble. F and G on input, given input X. So this is calculated with respect to the input. Okay, so this is nothing but the absolute value of cosine similarity. All right, so as I mentioned, we end up with a table like this. Here, we should read this table as follows. So if the similarity is small, then we have higher diversity and vice versa. By using this table, accelerated learning model is similar to our CNN model. We call that we have trained in an adversarial manner CNN. That is why our goal should be to detect models which are least similar to our pre-trained convolutional model. Next step is to generate augmented training data. Okay? So we actually create this data using fast gradient design method. The intuition is super simple. It is basically using gradient version of the cost function with respect to the input. It adds a small perturbation to the clean data. Here, X refers to our normal data, and we add like this epsilon. And we look at the gradient as sign of the gradient. So here, X double refers to our inversion, and then we have epsilon, which is perturbation one. After we created those examples, we augment those to the training process, and then we train our CNN, and we end up with that. This is how augment. Okay, so what about testing? How do we test? How do we make sure that we propose a better difference? It is using transferable, what we call transferable blind box attack strategy, in which the adversary does not need to know anything about the target model. So in these attacks, we have substitute model, and using this model, adversarial examples are created like this. Given clean data, we use our adversarial trained CNN to create perturbed data. Then we have some target models. These are trained models, which I should show you the details. Then we provide this perturbed data, and this will give us the perturbed error. So here, RMSE is error, so which is our error matrix. This rule estimation is actually a regression task. And we have this green arrow represents a clean test. And by using these two error values, we calculate a compromise, which is nothing but the RMSE perturbed divided by RMSE norm. Okay. So as our evaluation metric, we call resiliency, we calculate mean compromise. So in creating those perturbed test data, we might use different attack generation methods. Okay, so indeed we use multiple factors. So when we have more than one method, then we need to calculate the mean compromise among number of attacks. Okay, so here n corresponds to number of attack methods and number of parameters. As a data set, we have used publicly available NASA CMAPS data set, which is benchmark for rule prediction, which we have separated training and test data. The goal is to predict the remaining useful life before the engine failure. So here's a simulated engine diagram in this data set. We have different modules, compressor, combustor, turbine, and different sensors are placed on these modules, which provide our data. Okay? So in fact, this data set has 4 sub data sets. We have worked with one of the most complicated data. The first experiment we conducted is is to measure the impact of number of base learners in resiliency. Right? So the goal is to see what happens when we increase the number of base learners. So here we have the different colors correspond to different number of ensemble learners. So for instance, purple corresponds to 2 learner ensemble and yellow 3 learners. On the x-axis, we have the target models from CNN to LSTM. On the y-axis, we have the mean compromise value, which is our resiliency metric, as I introduced. Okay, what we can see from this figure is that when we go from 2 learner ensemble to 3 learner ensemble, we can see a significant mean compromise improvement, right? So what happens when we go from 3 to 4 learners? And some models, we even got worse results. So this means that, so the goal of this experiment is to find out optimal configuration for our proposed defense frame. So we have observed that adding more models after 3 does not bring a significant resilience. So we can conclude that we can select 3 learner ensemble for our defense. Okay, so the main experiment that we conducted is to compare our adversarial scheme with the non-adversarial settings. So the first one is white box setting, what we call. And here we create test data, perturbed test data, using a pre-trained model, and we do not transfer those examples. We use those model examples in the same model test. Black box setting, on the other hand, similar to what we are doing, except we directly use pre-trained CNN using clean data. This is the main. So here is the result. Here, each row we have a target model, and each column we have the training approaches, white box, black box, and our approach transfer. We can see that our method is always the best across different target models. And statistically, we were able to improve the resiliency by up to 97%. All right, to sum up, data-driven predictive utilize circumstances data to map those data to the real remaining useful values. However, these methods, specifically machine learning methods, are impacted significantly by small perturbations, small changes, which are constructed in a clever manner, significantly. So we end up with a really bad scenarios where we can end up with wrong predictive maintenance decisions, which can be quite costly. Here in this work, we promote diversity, promoting ensemble adversarial training, where our goal is to select the optimal subset of learners, and we experimentally show that our method can be an efficient defense mechanism against different adversarial attacks, where we statistically obtain up to 97% resiliency improvement compared to state of art training. Thank you so much for listening.